let's just go here. Point. Okay.
So,
I guess before we get started here, there's a cyber defense competition happening. Does anyone not know that, just out of curiosity?
Cool. I feel like that's such a point in that.
If you're not on a blue team, then we could always use your help on green team. Green team is pretty neat, pretty fun, and also very low demand. Basically, you show up on Saturday, you get free food, free snacks, free t-shirt, and all you have to do is log into stuff that's been getting hacked. So, fun. And then you get to sort of see there, you get to see the blue team struggling and suffering and getting paid by red team. And let's see anything else. But basically, on green team, you represent the legitimate users of the systems at the cyber defense competition. And you have to be able to do your job. So if blue team's logging out, you get angry at them and then take away their points. I'm going to do this real quick. I'm actually green team lead for this one, so...
Despite the red shirt.
Yeah, despite the red shirt. If you want, if you are interested in doing green team, or if you want to do the cyber defense competition, but you couldn't really find the time to get everything ready, get everything going, obviously, still maybe consider trying it out on blue team. Not too late, never too late. But otherwise, if you think green team is for you, then we'd love to have you right there all day Saturday. And by all day, I mean like 8 a.m. till 4. And if you're here before 8, then something's wrong with you. Alright, so I'm going to be doing a bit of a presentation here today about some really cool stuff. Anyone have any idea what binary exploitation even means? It's an awesome word, awesome phrase. It sounds badass. You got an idea?
I know what they are separately.
You know what they are separately? Will you put them together? Yeah?
I'm going to take a blind shot in the dark that if you see the binary entire string, you try and parse it out to figure out what it says, so you can crack it that way?
Nope.
Oh.
What it is it's breaking things without source code. You have no source code. You just have a program written in probably C. You know, if it's a program written in Ruby, you're not attacking the Ruby. You're attacking the Ruby interpreter that's written in C. And binary exploitation is basically it's the really elite shit. It's where you're going in. I wish I could get these mirrored. Now I can't see. Wait, maybe I can. You know what? Hang on. Can I get presenter notes on this? I can. No, I can't. Oh yeah. I can just do present with notes, right?
Yes.
With notes. That's there. Alright, now we'll be back online. I wish I could just slime for this. Does that work? Alright, this is much better. Alright, so binary exploitation is really elite, basically. It's one of the top things out there. It's a weird corner case. It's always the stuff that makes the news. 2 or 3 times in the last month or so, there's been a big news article. There was 2, right? There was the domain name one.
Talking about DNS,
Yeah, the DNS one. And there was like another one since then, wasn't there? Big binary vulnerability. And a lot of these all come out of all things that are really hard to do right in C, like not segfault. It's really hard. So what you're doing there is you're basically abusing memory vulnerabilities, mostly memory. Things like buffer overflows, buffer underflows, dangling pointers. Really, it's anything that ends up segfaulting your code because you did something wrong. Free after use, or use after free, rather. Free after use is fine. And the cool thing about it is any program can be a victim to this. I was talking about Ruby earlier. Well, you got a website written in PHP. PHP sucks. But if you do everything right in PHP, you're safe, right? Well, what if the web server has a buffer overflow? If you give the web server too big of a request, it might, something gets in the wrong place and it crashes. Well, binary exploitation is taking that crash beyond a crash and getting to take over the machine. There we go. Is that it? So most of what we're going to be focusing on here, and because most of what really ends up happening because of some reasons I'll get into in a little bit. Buffer overflows, very common. Well, not very, yeah, they actually are. They are very common because C is hard. C has, for the most part, a fixed size buffer. You don't, you can't just append some characters to a string and you get a bigger string. No, eventually you're going to end up somewhere else and it's going to segfault. Whenever you write more to a buffer than that buffer can actually hold, no, guess I'll just have to rebuff there. Whenever you write more than that buffer that can hold, you're going to end up writing somewhere else, and you're going to overwrite memory that's adjacent to it. You're going to overwrite maybe some variables that are next to it. You corrupt them, or if you're really tricky, you can maybe finagle in a way that'll let you read some other variables. That can be a lot of fun. If you're, you're supposed to be able to read your password, not supposed to be able to read the admin password, they're right next to each other in memory, you can maybe sort of smoosh them together, read the whole shebang. Lots of fun. Bypass all the things, right? And then there's some hidden fun stuff that you don't think about. There's a lot of other stuff in memory than just your variables. Big one is all that other stuff that makes up a stack frame. So if you haven't taken 288 or 381 or 308 yet, you might not know what a stack frame is. And basically, a stack frame is it's on a stack, that is a frame. But what it is, it contains all the context of a function. So that means it holds all of the, all the local variables that belong to that function, and all of the surrounding context of that function, which is mainly what function called it. So when we call a function, we create a new frame, we put it on the stack, and the stack grows down. I'm going to explain that in a bit, what that means. It's actually very, very important. Makes a lot of this stuff possible. And so you add a stack to the frame, and that's where the function is executing. It's executing in the context of that frame. And that frame has everything it needs to know when that function returns. We destroy that frame, and we just pop back up to the next frame, and we pick up where the function that called it left off. So as we call functions, we just build the stack, it gets bigger and bigger down. And then when functions return, the stack gets smaller. Those frames go off the stack, and then you're back left where you pick up where you left off when you called the newer function. The biggest important thing on the stack frame, or in the stack frame, is the return pointer. That return pointer stores the address of where you go when you return from the function. So if you're in at function A, you call function B. When function B returns, you really hope it goes to where it left off in function A. If it doesn't, you're going to have some serious problems. So here's an example of some stack frames up here. At the top, there's more functions all the way up until main, where it first started. And there's even some hidden fun stuff above main that you don't want to think about. Then down at the bottom, there's a bunch of old garbage. Never really been used. It might be used in the future. Maybe it was used in the past. Doesn't matter. At the top, we've got numerically higher addresses. So all ones or all Fs is up at the top, and 0 is towards the bottom. Up at the top. So we've got the return address here, then the saved base pointer. And I'll get into what these mean in a bit. Then all the stack variables that are on there, all your local variables, your buffers, your I that you're using to go through a for loop, those are all down in here. But then this function decided to call another function. So when it called another function, it saved its instruction pointer, saved that as the return address, then called into the green function. The green function saved the old base pointer, saved this here, then created a new base pointer pointing there, put all its variables on the stack, and then moved the stack pointer up here. There's a saved stack pointer in there somewhere, too. There's a bunch of saved stuff in there. But the gist of it is that every time you call a function, you save the return address, stack pointer, base pointer, create your variables, and then your stack pointer is down here, ready for you to call another function. You call another function, you save the stack pointer, save the instruction pointer, save the base pointer, call into a new function. And that's how the stack just keeps growing. And then, so when this green function finally decides it's going to return, what it'll do is it will shrink up the stack pointer, which gets rid of all these. These are gone now. It'll restore this old base pointer. It'll restore the stack pointer, and then it'll return, and then we're picked up right here where we left off. And now this orange, scary, unknown garbage variable stuff is right here, because the green is gone. It's disappeared. And how that fits into the big picture of everything else is with the maps here. So what we've got going on here, this is the entire memory address. This is everything that program can see. So we've got the code. This is where all of the instructions are. So yeah, it's coming out of the actual file that we're executing. And it's executable. Here we've got some read-write data also coming out of the file. So that's going to be a bunch of variables that are already initialized. Then we get the heap. That's where malloc puts things in these memory addresses. And then, notice we go all the way up to the tippy top, we get the stack at 7FFFFFDD000, which is, read write, it's the stack. So the stack, so what we get when we're looking at this is all the way down here, we've got memory address 0. That's null. Hopefully we never have a pointer to that we're trying to do something with. That would be bad. Then up here, around 4, 0, 0, 0, 0, 0, we have some instructions. So this is actually code. Or, as assembly language programmers will tell you, that it's text. It's instructions that the computer is executing. Then, we go up a little higher, we've got some data, some static data. Some of this is in the heap, some of it's actually in the binary itself, some of it's read-only, some of it's read-write, it's data. Then we've got a big gap of nothingness. And then all the way up here at 7FFFF, the highest memory addresses possible, we have the stack. And the stack keeps growing. But it grows down towards all this other stuff. So in here, we've got some frames. So we get, we'll say this is the frame for main. First function. Then here we've got the return address. And another frame. So we call it a function. Then let's say that foo called another function and popped its return address here. Thus the stack is growing down from higher memory addresses to lower memory addresses. So we've got another function, return address, and this function will have a buffer. It's got some stack variables, here's a buffer. And when I said it's important that the stack grows down, it's because the buffer is at a lower memory address than the return address. Which means that if we write more to this buffer than the buffer can hold, eventually, what are we going to overwrite? The return address. We overwrite the return address, what happens when the function returns? It goes somewhere really, really stupid. And then, we might not be executing this code anymore. We might be executing some data. What's in the data? Stuff we gave it. So that is basically how it all comes together. You load up some shell code. That's what we call when you got some code, some assembly language instructions. Throw them in data here. And it basically sets it up and it says, boom, give me a shell. Give me control of the box. So we write some code that says that. We load it up in the data. That's always pretty easy to do. Stick it in a web request, send it to the binary, standard input, whatever. Get some arbitrary data loaded in. Then, we overflow that buffer, we fill it up, fill it up, fill it up until, bam, we overwrite the return pointer, and we tell it, go execute my shell code. So then it goes, it executes your shell code, because as far as it cares, it's still running the same binary. And that's basically it. It's really fucking hard. So, let's do a case study. Boston Key Party, it was a CTF a couple weeks ago. A couple of us participated in. And there was one of the first challenges released that something like 150 people got within a few hours. So, not apparently that hard, but it took us 2 days. And basically it's a little calculator. I'll show you what that looks like in a little bit. Basically it pops up and it asks you how many calculations you want to do. You want to, let's say we want to do 10 things. And it'll be like, alright, do you want to add, subtract, multiply, divide? What two numbers? Then it adds them, subtracts them, does whatever. Moves on to the next one. It does the calculation. But they had a bunch of stupid, fun crap in it. Like if you put in a number smaller than 59, it just closes the application and says, you're using stupid numbers, I'm not going to help you with this. It yells at you if you do too few. It's basically really annoying. It times out if you have it open for too long. And the interesting thing about it is they give you the program. They do not give you any source code. They give you the program, however, so you can run it, you can analyze it, you can look at the assembly, which is a lifesaver. But then the one that you're actually trying to hack into is available over the network. So you connect into a netcat or telnet, and it's basically like you just ran it on your own console, except it's running on that server and you're connected to it from your own laptop. So the game there is obviously, you got to drop shell, turn that calculator application into remote shell. You can do anything. You can CD around, cat some files, steal flags. So real quick looking at it, a bit looking into it, crawling through some disassembly, looking at some instructions, lots of hard stuff, but basically what it does is it mallocs room for all your calculations. So if you say, I'm going to do 18 calculations, it mallocs an array that can hold 18 integers to hold all those results. Cool. It stores them in that buffer on the heap, and that's fine, that's perfectly safe. But then it has an array on the stack that holds 16 of them, so that's right here. So we got a nice big enough array in here, but then an array that can only hold 16 there. And then for, I got no idea why, they just copy it to the stack before you exit with memcopy. And that means that, so this holds 16. Well, there's a couple little things here like that base pointer, the stack pointer, maybe another variable. But the 19th thing that you put in that 16 element array plops right onto that return address. So, there we go. All right, we got this. It'll take like 20 minutes now to actually exploit this because we can get segfault, we can get to jump anywhere, we can get to execute any code, right? So, attempt number one, let's get some shell code. And that's what I told you about earlier. So, wrote up some code right there. What that does is it loads up 59, or hex3b. Almost everything in here is hex, by the way, even if it doesn't have 0x before it. So it loads a 3b into RAX, which is a register. It loads this pointer, which is a pointer to the string /bin/sh into RDI, first argument. Our SI, second argument, null. Our DX, third argument, also null. And then we do the syscall instruction, and it's the equivalent of doing that in C. Anyone have any idea what that does in C? Quit whatever you're doing, give me a shell. Sounds fun. So it's not calculator anymore, it's bash. So if I do that over the network, I've just got a shell in there. It's like I'm SSH'd into the box. And there's a lot of things that I'm working on. So I get the string literal bin.sh. I can get that on the heap by adding the right numbers together so that it adds up to /bin/sh in ASCII. And as I'm working on this, I'm going through it. It's really, really cool because malloc is always putting the buffer at the same place. Which is awesome. I don't need to worry about it, right? Yeah, that's a wonderful sign of some head banging to come. So to get my shellcode injected, basically I had that shellcode from back here. It's an array of characters, an array of bytes. I need to convert that into integers. Now this particular machine, an int was 4 bytes long. So convert those. One, there's mixed instruction length, so it's not like each instruction is 1 integer. No, that's 7 bytes. So each instruction is an integer and 3/4. So I gotta then separate those all up into the right length. And then endiness came to bite me in the ass. So if I wanted to have, 48 C7 C0 3B 0000048, I need to have 3B C0 C7 48 48 00 00 00 8C B0 C7 C7 48. This weird order. Basically, it's like switched and then switched, turned inside out. Get bit in the ass, banditas. And then I need to do the same thing with that string, because the string is just a bunch of single byte characters. Need to be grouped into 4 bytes and then reversed in place. So it ended up being /bin as one int and /sh as another int, effectively in the order of NIB/ null HS/. So endianness, and then convert the int arrays into decimal, from hex, which is fine, that was easy, and then break it apart into calculator operations without using any numbers smaller than 39. That was just pure evil. But finally I got a nice little thing copy-pasted up, and threw in some empty operations to pad everything so that lands on that 19th spot. String literal gets loaded in memory right there. Shellcode begins in memory right there. And then overflow the buffer so that that value lands on the return pointer. Hits my shellcode, executes, done, right? Now fail. Bunch of stuff went wrong. So take a look at the real map of what's going on here on the program when it's not running inside GDB. Well, A, the heap is not executable. No execute bit. It's just like the permissions that are on files. If there's not an X, you can't execute code that is at those memory addresses. Son of a bitch, right? So I can't do my shellcode in data. I have to do my shellcode in here. Or I have to add the execute bit to here or there or somewhere weird. And those are scary numbers. That's not FFFFFFFFF. That's weird and frightening. And also, the heap is randomized. So everything's at random addresses, and if you've ever heard of ASLR, address space randomization. ASLR, it does this, it randomizes it, which is specifically to make things like this very, very difficult. Because now, I don't know where my shellcode is. And also, my shellcode's not even executable. So, there was a lot of digging there, trying to find a way to make it executable, trying to find ways of doing all of these weird tricks to try to figure out where it did end up getting put. Lots of different things. If I, my shellcode's somewhere random in this, which is, how big did I say this was? How much memory does Linux? It's several petabytes. So several petabytes of space in here. That my shellcode's somewhere. I don't really know where, but it's in there. Got to find it. Then I got to make it executable. And all this stuff is very, very hard, and it basically didn't work. So, I decided to do it the hard way. And the hard way is using a little trick called return-oriented programming. And basically, when you think of the way a normal program works, you do some instructions in a row until you have a call instruction, where you jump to a function, you do that function, and then you return to where you left off. And it doesn't really matter. You can call the same function from a bunch of different places. It always goes back to where you left off. That's normal code. That's code that doesn't hurt your brain, right? Call a function, the function returns to where it was called from. Well, with return-oriented programming, what you're doing is you're treating the return instruction as a jump instruction. Because you preload the stack with a bunch of addresses that you want to return to, and then you hit return, you jump somewhere. So instead of, running through your program nice and in order, where you're going through, you're hitting a call, doing something else for a while, and then coming back. So you think of a function as a beginning and a return. The function and for the most part, if we call, we're going to call where you go here. So we're going to return where you come right back there. But if we call in here, we're going to go there, turn there. We'll call it again. All pretty sane. Well, with return-oriented programming, what we're doing is we're rigging the stack so that that does not happen. And we never really do another call. We only do returns. So we've got our stack full of return addresses. And we hit the return. We get this address, which takes us to here. Does a couple of things, and it returns us to this address, which is here. Does a couple of things, hits another return statement, goes somewhere else. Basically, it's a way of rewriting the entire program while it's already loaded. So you do some stuff, and we call it gadgets. It's a couple of instructions, maybe a pop, maybe a move, maybe an add or subtract, then a return. So we return, which is really just an arbitrary jump to anywhere we want that we've planned out ahead of time. We jump there. We do a couple of things. We hit another return. So we jump somewhere else in the program. And we're using all of the instructions that are already in the program and rearranging them in a weird order, using only the ones that come a little bit before a return. And so, you know, it's pretty convoluted and just a crazy way of rewriting everything the program does just by choosing where it goes when it hits return. So the goal of doing this ROP gadget is to basically load those values, load that 59, load that pointer, load those two nulls in those 4 registers, and then hit a syscall instruction. We need to do that. So we got to find some gadgets, right? Well, right here, here's a memory address in that code segment that has a pop RAX and a return. I can do that. I can put that 59 on the stack. Then I can load the return address so it jumps to this. It'll load that 59 off the stack into the register, and then return, so I can go somewhere else now. It's not a return, it's really a jump now. So then it'll jump me to here, where I'll pop RDX, so that can get my value that I put on the stack ahead of time into the D register. And then, same thing into SI. That was actually a bonus, it does 2. Saves me some work. Then returns, goes somewhere else in the program. But there was no instruction to pop RDI. I didn't have any way of loading the null byte into this register, and I couldn't just leave whatever junk was in there before. The syscall failed, it yelled at me about a seg fault, the program crashed. But there was no pop RDI instruction anywhere in the binary. And I was looking for weird ways, maybe it's something that moves into RDI, some way that I could, you know, like XOR something, XOR RDI with itself. That'll always get you 0. I just need to get a 0 into that RDI register. No way to do it. I was stuck. But there was one more trick. x86 variable length instructions. So, retq is just C3 in hexadecimal. So pop RSI is just 5F. That's just 2 bytes. So that means if those 2 bytes come in a row, anywhere in the program, I can pretend it's an instruction. So I actually found it right here in the middle of this pop R15 instruction. But when we cut off the first byte, it's really just pop RSI. Pop RDI, sorry. I might have got something mixed up there. But basically, we go all the way back, you know, to look at my shell code. Oops, wrong way. You know, like these are big multi-byte instructions. If there's a single 1-byte instruction, there could be an instruction there. There could be another instruction here. You know, this is an instruction. That actually is, I believe, a return right there. It's not because it's in the middle of another instruction, but it could be. So, found it right there, and I was in business. I got all my gadgets. I just had one more piece to fill in, and that was getting that string literal, that /bin/sh. I need that string somewhere in memory that I can get a pointer to it. So the heap and the stack are randomized. I don't know where the stack is. I don't know where the heap is. So kind of screwed. Can I try to de-randomize it? There's a couple of tricks that you can use to de-randomize the stack. But the thing is, you know, they didn't look like those vulnerabilities were there. And once you started ROP, you're pretty much committed to doing ROP because the program is boned. You're jumping around all these weird places. It's returned 14 times without a single call. It's not going to go back to normal. But then finally, I was digging through the assembly for the 85th time, and the X and Y operands, so when you add 2 numbers together, you give an X, you give a Y, those are actually stored in a global variable, a static global variable in the data segment that's always the same space. And the X and Y are right next to each other. Well, I already know that /bin/sh is exactly 8 bytes, so it fits perfectly in 2 4-byte integers that are next to each other. I just have to sort out the emptiness, of course, and then I am in business. I got everything sorted out. So my RAX gadget that loads that first register is at this address, and then it returns. I'll take this address, which loads that one, then that will return to this address, which will load DI and D. That's not a real register. What's that supposed to be? Anyway, then this will return to the syscall. Syscall happens, and boom, executes bin/sh, which that literal is loaded into this memory address always. So I built the stack, and what the stack I want looks like, it looks like this. there's a lot of zeros in there. That's because the registers are 64 bits, integers are 32 bits. So you basically have a 32-bit integer and then a 0 to load a 64-bit register. So at the, I guess this is the bottom of the stack or the top of the stack, depending on how you look at it. This is the last thing to come off the stack. And this is the first thing to come off the stack. And I line it up in this buffer so that this lands on the return address. And then the function finishes executing, finishes doing its job. Do you have a question? Or just stretching?
No.
Clearly doesn't have a question. All right. So fills up the buffer. This int lands on the return address, which takes me to those gadgets. Takes it to this gadget, which pops these two values and fills up dx and di. Takes me to, and then I do another return, pops this, takes me to this gadget to pop into RDI, which pops that string pointer. Then takes me to the next gadget, takes me to the next gadget, then finally takes me to syscall instruction. And I got it. Drop shell. So I'll show you what that looks like. On my laptop. What's it on my mouse? Okay, so here's that calculator application. I connected to it over the network with Netcat. Let's see. There we go. And let's see, let's tell it we want to do 3 calculations. It actually yells at me because it doesn't like the number 3. So we'll do 5. Oops. 5 calculations. All right, let's add 100. All right, whatever. So it's a calculator, right? Then when we do an invalid operation, it just yells at you. Unites it. All right. So I took that, I took all those numbers that I know I need to add together to fill up that buffer, right, that everything lands in the right place. And what happens is get in my copy paste buffer here. Tells it I want to do 80, which is way too many, and then fills it up so that everything lands there. The other thing is, so I fill up my buffer, then I'm here, and I have to have that stack I built with all my gadgets and everything goes up this way. So I need to have plenty of room to do that. Connect to the calculator, paste my stuff in, and I have a shell.
You scroll up, it shows what you pasted in.
Yeah, I can actually pull it up here. It's kind of nonsensical.
Okay. Well, it's better.
That. What it is, I tell it I want to have room for 80 things in the buffer, even though there's only room for 16.
Yeah.
Then a bunch of invalid operations that end up putting zeros into it. And if I scroll up a little, here's actually that stack that I built that has the the various addresses of gadgets. It's up here before I've converted to decimal. Convert to decimal, string literal, switch endianess. That's basically how I work because I built it because I don't know how to use. There are tools for making this easier, but they kind of make it easier for the most part. You still have to do all this work. They just take out some of the hand converting from hexadecimal, fixing in units and whatnot. So there's my stack, convert to decimal, and then the end result, so I put it in is 80 things, a bunch of invalid operations that fills the buffer up with zeros and takes me to the return address. Then the return address that's add these two numbers together that when added together get me that number I need to drop in the return address, taking me to the first gadget. Then the rest of this is basically it's alternating back and forth between the value that I want to load in the register and the address of the gadget that will load the register. And when that gets pasted into it, that all happens, and you get shell. See? All right. Any questions? Anyone want to talk about some of this? That wraps up the presentation. It is a lot of fun. It is very, very painstaking, but it's fun. Yeah.
So if someone wants to learn how to do this, how can they learn? Where can they look for that?
Okay, there is. You said you found something, Matt, that was good. The website thing, or did it kind of suck?
What website thing?
Over the wire.
Over the wire.
Yeah, it starts with some basic like buffer overflow stuff. I think those ones even start with the stack marked as executable. So that first example he did with the shellcode, that'll work because that's easier. And once you understand the shellcode, ROP is not that big of a step, but it can seem really daunting just to like look straight at the ROP Gadgets. So.
Yeah, ROP Gadgets is. I knew it would work, but it still took me 2 days to try it because it was scary.
Yeah.
So over the wire.
War Games is another one.
Smash the stack.
Smash the stack.
But those are basically places where you can go to play around with this and try it out. If you want to learn, the biggest thing that I can say is learn how to use GDB. Has anyone used GDB before? Does anyone like really love GDB and know it's the best thing ever? It is. It is the best thing ever, and it can do so much more than what you think. I can actually show you real quick.
Yep. It's not like it.
Oops. So it's pretty simple, right? We can break it main and run it, but we can even do a disassembly of it right there. We can see what the registers are. We can even look at data. There's the 32 first 32 integers that are on the stack, and it's really critical for doing stuff like this to be able to fly around between the disassembly and other things. And then even when you get your shellcode loaded in, you can use GDB to make sure that your shellcode is actually loaded in, because GDB can disassemble your shellcode for you. And if it's what you think it should be, then your shellcode got loaded right. If it's not, then it isn't. But yeah, learning GDB is absolutely huge if you want to do stuff like this. Other questions? Yeah?
So GDB is a debugging tool for any binary executable, or?
Like anything. It's kind of frightening.
Just about anything until let's see, or even lower than that.
Yeah, it can. It can be used for a lot of interpreted languages too, because of how debug symbols work. You can use it to debug the interpreter, but C and C++ are the first class citizens there, or even handwritten assembly. There was another CTF 2 weeks ago, a week ago, something like that, that had a bunch of handwritten assembly that GDB could debug just fine, even though it had never been C. It was handwritten assembly. You can debug like a freaking Arduino with it. You actually can. It can do embedded hardware, and almost everything is built on top of GDB. Eclipse's debugger is really just on top of GDB and doesn't let you do any of the cool things. So if you learn GDB, it's quicker and easier to do it through GDB on the command line than it is to use any tools, and of course way more flexible. Yeah?
And where would we go to learn how to use GDB? Silence.
Man pages, get really desperate and Google how to do what you want to do in GDB.
Yeah, there's a learning curve, definitely.
There is a massive learning curve to GDB in the 2 days that I was working on this, I learned probably 3 times as much as I already knew about GDB. I learned in those 2 days, just from desperately needing to be able to read the next 80 things that are on the stack. I need to know how to do that with GDB, so I Googled it.
Yeah, that examine thing is really useful.
Yeah, X32 hexadecimal words beginning at the stack pointer. So there's the stack pointer. See, stack pointer, 630, 630, and 32 words. Hugely important. Or, I can even do. It can examine things as strings. So let's just see what the first 12 strings are at the stack pointer. There's probably no strings. It's a bunch of stuff that's not a valid string, obviously. The instruction pointer, once again, a bunch of stuff that's not valid strings. But instead of examining with strings, let's examine with instructions. Look, it's instructions. And those are the right instructions, yeah. And it even tells you, like, when you're loading a weird pointer, it actually will tell you if that pointer is pointing to something you can figure out. Like there, it's loading standard in and standard out pointers. Hugely useful, especially the examine thing. That was life-changing.
Yeah.
And frame information is also huge when you're first trying to pull off a buffer overflow. Tells you stack level, where the frame starts, where the instruction pointer is. This is the return address. So when that changes, you know you've done something right. Save stack pointer, save registers, stuff like that. GDB is amazing and useful.
Did you say anything about breakpoint?
Oh yeah, B star. So if you've ever
You
used
started,
GDB
like,
for like lame things, you've done break,